Hello everyone, I hope you all are good. So today we are going to discuss about electrostatic potential and capacitance NCERT Exemplar 2.14 to 2.23. Disclaimer. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. Okay, so example problem 2.14. Consider two conducting spheres of radii r1 and r2 where r1 is greater than r2. So it means sphere with radius r1 is larger. If the two are at same potential, if both the spheres are at same potential, the larger sphere has more charge than the smaller sphere. State that whether the charge density of the smaller sphere is more or less than the larger one. Okay, so if two are at same potential, if both the spheres are at same potential, at the larger sphere, that is of r1 radius, has more charge than the smaller sphere. State whether the charge density, that is, which charge density they are talking about here, surface charge density of smaller sphere is more or less than that of larger one. So we have to compare the surface charge density of both the spheres. So I will give you some time to think about it. So again question here. So let's see the solution. So what is the thinking process for this question is, electric potential on the surface due to their charge need to be written in the terms of their surface charge density. So the electric potential due to these charges that are on these two spheres of radius r1 and r2. So electric potentials on spheres due to their charges need to be written in the terms of their charge densities. Okay, so firstly we will write the potentials in the form of charges and then we will convert the equation in the form of surface charge densities. Since the two spheres are at same potential, therefore, so since they are at same potential, then kq1 upon r1 equal to kq2 upon r2. So what is q1? Charge on sphere having radius r1 and q2 is charge on sphere having radius r2. Okay, so these are the formula for potential. So potential, if the two are at same potential, so potential, this is the formula for potential. Potential on the surface of first conductor and on the surface of second conductor is equal. Okay, so by equating them, now we can reduce this equation or reduce this expression in the form of charge densities. So this charge is present here, we have to only want here area of the spheres. Okay, so we want to reduce this expression into surface charge density. So let we assume that in this equation, in this formula, first formula for sphere 1, we have to multiply by r1 and divide by r1. So it will become kq1 r1 upon r1 square. Okay, and multiply this term with r2 and divide by r2. So it will become kq2 r2 upon r2 square, and also divide on both sides with 4 pi. Okay, so we can divide here. This will cancel out if we want to. Okay, so we will divide on both sides with 4 pi. So now 4 pi r1 square, what it will become? Area of surface area of first conductor, and what it will become? Surface area of second conductor. Okay, now charge upon area we have achieved. So we want to reduce this expression, this one, to the expression of surface charge densities. So we want area here. So we have to do something that will bring area in the denominator on both sides. So firstly we will multiply or divide with radius. Okay, and then divide both sides with 4 pi. Okay, so these are the steps. And I will also explain with the help of diagram. This is first sphere having radius r1, and this is second sphere having radius r2. Okay, since r1 is greater than r2, which means this is bigger sphere. Okay, and there is some charge q1 on this surface, q2 on this surface. Okay, so we want surface charge density. So what is surface charge density of this conducting sphere? q1 upon 4 pi r1 square, and this is the sigma 1. And what is the sigma 2 surface charge density of second sphere? q2 upon 4 pi r2 square. Okay, so we want to reduce this expression into this. So we want this in the expression. So we are given that potential is same on both the conducting sphere, surface of conducting spheres, that is kq1 upon r1 equal to kq2 by r2. So now how we will reduce this, I have explained. Okay, we want this thing below. Okay, so now this thing we have achieved, or we can write now this q1 upon 4 pi r1 square is sigma 1. K and K will cancel out from both sides. This K and K will cancel out from both sides. Then q1 upon 4 pi r1 square is sigma 1. q2 upon 4 pi r2 square is sigma 2. So sigma 1 r1 equal to sigma 2 r2. And after rearranging, sigma 1 by sigma 2 equal to r2 by r1. Okay, this thing we have reached. Now in question it is given that r1 is greater than r2. Radius of first sphere is greater than second sphere. So radius of first sphere is greater than second sphere. Since r1 is greater and r2 is less than r1, so this ratio r2 by r1 will be less than 1, because r2 is smaller than r1. So smaller value is in the numerator. So this ratio will be less than 1. This means this sigma 1 is also less than sigma 2. Okay, so this means sigma 1 is also less than sigma 2. So sigma 1 is the surface charge density of the first sphere, which is larger. So surface charge density of larger sphere is less. Surface charge density of smaller sphere is large. Okay, so charge density of the smaller sphere is more than that of larger one. Okay, so this is the surface charge density of smaller sphere, which is more than that of larger one. Okay, next question 15. Do free electrons travel to region of higher potential to lower potential? So do free electrons travel to region of higher potential or lower potential? Okay, so we have to identify that electron moves in the electric field in the direction of opposite to the electric field, not in the direction of electric field. Positive charge move in the direction of electric field, but electrons are negative charge particles, so they move in the direction opposite to the electric field. So electric field is from higher potential to lower potential. Direction of electric field is from higher potential to lower potential. Positive charge move in the direction of electric field, so it will go from higher to lower potential. But negative charge move in the reverse direction. So let's see the answer. So I will give you some time to think about it. So again question, solution. So the answer for this question is the free electron experience electrostatic force in a direction opposite to the direction of electric field. Okay, being is of negative charge. They are negative charge particle, so they will experience force in the direction opposite to the direction of electric field. The electric field always directed from higher potential to lower potential. Direction of electric field is such that it goes from higher to lower potential. Therefore, electrostatic force and hence direction of travel of electron is from lower potential to region of higher potential. So electron move in the direction opposite to the electric field, and electric field is in the direction of higher to lower potential. So electron is in reverse direction, so they will move from lower potential to higher potential. Okay, so they are asking, do free electrons travel to region of higher potential or lower potential? So electron travel to region of higher potential. Okay, so electron travel from lower to region of higher potential. Okay, next question 16. Can there be potential difference between the two adjacent conductors carrying the same charge? Okay, so can there be potential difference if there are two adjacent conductors having same charge? Can potential difference exist between them? So let's see what is the solution. I will give you some time to think about it. So what is the thinking process for this question? The capacity of conductor depends on its geometry. We know that capacitance of a parallel plate capacitor we have seen. Also, if there is only one conductor, then capacity of this conductor to store charges depends solely upon its geometry. Okay, so what is the dimensions of the conductor? The capacity depends on that. That is length and breadth and any other measurement of the dimensions. For a given charge, potential is inversely proportional to the capacitance. We know that Q is equal to CV. Okay, so V is equal to Q by C. So if there, for a given charge, if we fix the charge, then V is inversely proportional to capacitance. So two adjacent conductors carrying the same charge, if they are carrying the same charge, they may have different potentials, and it is dependent upon capacity of their capacity. If the capacity of two conductors is different, then there will be potential difference between the two conductors. Their potential will be different if their capacity is different, even if the charge on both the conductor is same. Okay, and on which factor capacity depends? On geometry or dimensions of the conductor. So answer is yes, if the sizes are different. Okay, so potential difference will be there if sizes are different. If sizes or geometry or dimensions of conductor are also same, then it means their capacity will be same, charge is already same, then we can say there is no potential difference between two adjacent conductors, so they are at same potential. But they have only given that they have same charge, but didn't say anything about the geometry or capacitance of the conductor. So since capacity of conductor depends on geometry and geometry can be different, so capacitance can be different for both the conductors, therefore there may be potential difference. So there may be potential difference, yes, if the sizes are different. Okay. Next question, can the potential function have a maximum or minimum in free space? Okay, so the potential function that is in free space where there are no other charges, so can potential have a maximum or minimum value? Okay, so can potential have maxima and minima there? So let's think about it. I will give you some time. So let's see what is the solution. So the answer is no. The absence of atmosphere around the conductor prevents the phenomenon of electric discharge or potential leakage, and hence potential function do not have a maximum or minimum in free space. So there is no, in free space there is no atmosphere, there are no any other charges present. Okay, so this prevents the leakage of electric. So this prevents the leakage of electric potential. Okay, and also restricts the electric discharge. Okay, and hence potential function do not have maximum or minimum in free space. Okay, so if there is zero electric field in the atmosphere also, so it means dv by dr is equal to 0. So which means potential is not changing, potential is constant throughout. So potential is constant, so there is no maxima or minima in the space. Okay, even if potential is varying, but it is varying smoothly. Okay, so there is no sharp maxima or minima present in the free space. Okay, either potential is constant or varying smoothly. Eighteenth question, a test charge q is made to move in an electric field of point charge capital Q along two different closed paths, figure 2.6. First path has section along and perpendicular to the lines of electric field. So this is the first path having is along and perpendicular to the lines. This is the electric field line, so it is perpendicular to the electric field lines. Second path is rectangular loop. Second path, this path is rectangular loop of the same area of the first loop. So they both these loops have same area enclosed in there as the first loop. How does the work done compared in two cases? So what is the work done compared in two cases? Okay, so there are two closed paths. First one is has section along and perpendicular to the, these two sections are along the electric field. These two sections are along the electric field. Electric field is radially outwards, na? Okay, so radially outwards, and other two sections are perpendicular to electric field. They are in this direction, so this is perpendicular to electric field. Okay, and other rectangular loop of same area is present here. Okay, so both the loops are closed paths. Okay, so we have to compare the work done in two cases. So I will give you some time. So again same question, and solution is, So answer for this question is, as electric field is conservative, work done will be 0 in both the cases. Okay, why? So we know that these are closed paths. Okay, that's why I emphasized on the word closed when I recited the question. Okay, so enclosed path means if we are starting from here and after going from there and returning to the same point. Since electric field is conservative, this means the work done by the charge only depends on initial and final positions. So if we are starting from here and after moving along this loop, we again come at this point. So initial and final position is same. Okay, so work done depends upon initial and final position because electric field is conservative in nature. So initial and final positions are same, so work done will be 0. And same for this loop. If we are starting from any point, let's see from here, and after completing the loop and coming here again, so initial and final positions are same. That's why work done is 0, because electric field is conservative and work done depends upon initial and final positions. Note, conservative forces like electrostatic force or gravitational force are those forces work done by which depends only on initial and final positions of object, and object here is charge, but not the path through which it goes from initial position to final position. So it doesn't depend upon path. Okay, so we can also follow the another path, any other path, which is here, from here, from here, from here. If we are coming again at same point, work done is 0. Okay, so short answer type questions. Prove that a closed equipotential surface with no charge within itself must enclose an equipotential volume. So it means that closed equipotential surface, any enclosed equipotential surface with no charge within itself, must enclose an equipotential volume. Means the bulk inside the equipotential surface should not have any charge within. So we have to prove this. Okay, so I will give you some time. So if there is equipotential surface, so the volume enclosed by that equipotential surface must enclose no charge within. Okay, so we have to prove this. So how we will prove this? According to Gauss law, there are no charges enclosed. If there are no charges enclosed by a surface, the net electric flux through that surface is 0. Okay, so according to Gauss law, if there is no charge enclosed by a surface, then net electric flux through that surface is 0, because electric flux according to Gauss law is equal to charge enclosed by epsilon naught. So if there is no charge enclosed, then electric flux will be 0, or if electric flux is 0, charge will be 0. Okay, so mathematically this is expressed as electric flux through any enclosed surface equal to closed integral over that surface E dot ds. Okay, so electric field dot area element and enclosed surface over whole surface. Okay, so which is equal to electric flux is equal to Q enclosed, charge enclosed by epsilon naught, which is 0, because we have to prove now that there is no charge enclosed. So if there are no charges enclosed, electric flux will be 0. Since Q enclosed is equal to 0, it implies that electric field E must be 0 anywhere inside the surface S. Okay, so if Q is equal to 0, which is and we have to prove what? That it must enclose an equipotential volume. Okay, what is equipotential volume? Which means over a volume there will be constant potential. So they are asking that if any equipotential surface closed and volume enclose and any volume, then with no charge within itself, it must enclose an equipotential surface. It means potential inside that surface should be constant everywhere. Okay, so since Q enclosed is 0, it implies that electric field must be 0 everywhere, or electric flux will be 0 inside the surface, or electric flux will be 0 through that surface, and electric field must be 0 everywhere inside the surface. Okay. Okay, let's see. This is any equipotential surface. Let's take the simple case. Very simple case of sphere. Okay, this is equipotential surface. There is some charge due to some charge outside or on the surface. Okay, so this is equipotential surface having constant volume over the surface. Okay, so over the surface this potential is constant because this is equipotential surface na? So potential should be constant over the surface. Okay, so they are asking that with no charge inside, so there should not be any charge inside, so it must enclosed this whole volume. It must enclosed an equipotential volume. What is meant by equipotential volume? It means inside this surface, means the volume inside this surface should also have constant potential. Okay, so volume inside this equipotential surface should also have potential equal to constant. Okay, so we know that if there is no charge present inside, so electric flux through this surface will be 0 according to Gauss law. Okay, so electric flux is 0, it means electric field is also 0 inside this surface. Okay, the electric field is related to the electric potential V. Now, how electric field is related to electric potential? E equal to minus dV by dr. So E equal to minus, so this sign, this inverted delta, it means gradient. Okay, it means d by dr. Okay, so d by dr, so it will become dv by dr. So this inverted triangle means gradient, d by dr. Okay, so E equal to minus dv by dr, or we can say minus of gradient of potential. Okay, so d by dr is called gradient. So this is the relation of electric field with potential. So if electric field is 0 inside the conductor, okay, if there is no charge, then electric flux through the surface 0, also electric field inside the surface 0, and if electric field is 0, this means the gradient of the potential is also 0, means dv by dr is equal to 0. Therefore potential must be constant throughout the volume enclosed by the surface S. So if dv by dr equal to 0, it means potential is not changing inside the volume for any 2 points. This means potential is constant inside the surface, that surface, equipotential surface. So potential is constant for any point inside this surface. This means this surface is enclosing an equipotential volume, means throughout the volume potential is constant. Okay, so therefore the potential must be constant throughout the volume enclosed by surface S. Got it? Next question. A capacitor has some dielectric between its plates and capacitor is connected to a DC source. The battery is now disconnected and then the dielectric is removed. State whether the capacitance, the energy stored in electric field charge is stored and voltage will increase, decrease or remains constant. So let me read this question parts by part. Okay, so capacitor initially capacitor has some dielectric between its plates and the capacitor is connected to a DC source. Okay, so capacitor is connected with DC source having dielectric between its plates. This is the initial condition. Now condition changes now. Now battery is now disconnected. First thing, then dielectric is also removed. Okay, so both the things that are mentioned in first case are removed. Battery is now disconnected, also dielectric is removed. Okay, state whether the capacitance, the energy stored in it. So all things you have to mention in the answer. So whether capacitance or energy stored or electric field or charge stored and the voltage, these 5 things will increase, decrease or remains constant. So effect of these 2 things, disconnection of battery or removal of dielectric, on these 5 things will be mentioned in the answer. Okay, so let's see. So I will give you some time to think. So what is the thinking process for this question? Here the charge stored by the capacitor remains conserved after its disconnection from the battery. Even if we disconnect the battery, the charges stored will remain conserved. Okay, according to the conservation of charge. Charges just before the disconnection of battery will remain constant. That value of charges will remain conserved even after the disconnection of battery. Okay, so let's see the answer. The capacitance of parallel plate capacitor filled with dielectric medium of dielectric constant K is given by. Now, initial case, when there is a dielectric between the plates of capacitor, also it is connected to DC source. So what is the capacitance now? We have to see. So capacitance is equal to K epsilon naught A by D. Okay, so capacitance with dielectric medium between its plate and also battery is connected. So capacitance will be K epsilon naught A upon D, where signs are as usual. Okay. The capacitance of the parallel plate capacitor decreases with the removal of dielectric medium as for air or vacuum K equal to 1. Okay, so now we take first case when the dielectric is removed from the plates of the capacitor and now there is only air between the plates of the capacitor. Okay, so now K is replaced by 1. Why? Because we have removed the dielectric medium. Okay, we have removed, dielectric is removed, we have removed the dielectric medium. Now K in the equation is replaced by 1. Okay, for air, because now there is only air between the plates of capacitor. Okay, after disconnection, now firstly we remove the dielectric, now we are disconnecting the battery. After disconnection of battery, charge store will remain the same, but due to conservation of charge. So due to conservation of charge, charges will remain conserved. Okay, charges will not change after the disconnection of the battery. So the energy stored in an isolated charge capacitor equal to Q square by 2C. This is the formula for energy, Q square upon 2C. Okay, so energy stored in an isolated charge capacitor Q square by 2C, as Q is constant. Now because Q is conserved according to the conservation of charge, so energy is dependent upon what? Upon capacitance of the capacitor, and energy stored is now inversely proportional to the capacitance only because charge is conserved. Okay, and C decreases with the removal of dielectric medium. Now C is decreasing. C decreases. Why? Because we removed the dielectric medium. Therefore, energy stored increases. Okay. Since Q is constant and V equal to Q by C, so Q is constant and potential is given by Q by C. Q is constant, conserved. So V is also inversely proportional to C. As C decreases, so in turn V increases. Okay. And therefore E also increases because E equal to V by D. Okay. So what happened? State whether capacitance. Capacitance is decreasing. Energy stored is increasing. Electric field is increasing. Voltage is also increasing. Okay. So we got all the answers. So I will explain some more. Like this is the capacitor initially. Having dielectric plate, having dielectric between its plates of any dielectric constant K. Okay, so it is also connected to the battery. After that, we removed this K. So in this K, C is equal to K epsilon naught A upon D. Now we removed the dielectric constant. Okay. We removed and also disconnected the battery. So capacitance, now we remove the dielectric. Now there is air between its plates. And K for air is 1. So it will become epsilon naught A by D, which is less. Okay. So after that C dash is less than C. So capacitance decreases on the removal of dielectric medium. Okay. So as capacitance decreases, energy was Q square upon 2C. Q is conserved. Okay. So after disconnection of battery, Q is conserved. Q will not change. Okay. So Q is not changing. Also battery is disconnected and dielectric is removed. So Q will remain constant. So energy is inversely proportional to C. Okay. So as C is decreasing, it means this energy will increase. Okay. Second thing, potential difference between the plates is equal to Q by C. Since Q is conserved, V is inversely proportional to C. So as C is decreasing, so this potential difference will increase. Okay. So V increases. So also electric field. Okay. This is energy. So you can also use U here. Okay. So this is energy. So I am writing now for electric field V by D. Okay. So as V is increasing, so electric field will also increase. Okay. Note, one of the very important question with the competitive point of view. So these are one of the very important questions with the competitive point of view. Okay. So these conceptual questions are generally asked. So next question, prove that if an insulated uncharged conductor is placed near a charged conductor and no other conductors are present, the uncharged body must be intermediate in potential between that of charge body and that of infinity. Okay, so what they are asking and saying, so we have to prove that if an insulated uncharged conductor is placed near a charged conductor, so there is a charged conductor which is placed anywhere in the space, okay, and another uncharged conductor is placed near that charged conductor, okay, so and no other conductors are present beside these two conductors. The uncharged body must be intermediate in potential between that of charged body and infinity. So the body, that uncharged conductor, must be intermediate in potential, means its potential will be intermediate between charged body to that of charged body and to that of infinity. Okay, at infinity we consider the potential to be 0, and there is a charged body, it will have some potential. Okay, so uncharged body will have, should have intermediate potential. We have to prove this. Okay, so I will give you some time. So let's see the solution. So this type of arrangement is there. One charged conductor is placed in the space. Okay, so this is infinity. Okay, so this electric field is uh exist up to infinity. Okay, so an uncharged conductor is placed anywhere between this conductor and infinity. Okay, so no any other charges are present. So this electric field from this charged conductor having direction in this direction. We know that electric field having direction in decreasing potential. Okay, so direction of electric field in such a way that it goes from higher potential to lower potential. So potential at the surface of this conductor, so potential at the surface of this conductor is very high. Okay, so it decreases as we go away from this conductor. At infinity it will be 0. So this conductor is placed between infinity and this charged conductor. So this uncharged conductor will be having potential intermediate between this as that of that charged conductor or infinity. Okay, if an uncharged insulated conductor is placed near a charged conductor, the uncharged conductor will get some induced charges and electric field of charged conductor. Okay, so these type of charge distribution will appear. If an uncharged insulated conductor is placed near a charged conductor, the uncharged conductor this will induce charges like this due to external electric field of this charged conductor. So negative charge particle will appear in this direction and positive charge particle will charges will appear in that surface, and electric field of charge conductor will continue till infinity as shown in the figure. So this electric field due to this charge conductor will continue till infinity, and potential near the surface of the charge conductor is very high. Okay, and potential at infinity is 0. So this charge conductor is placed anywhere between this charge conductor and infinity, so it will be at intermediate potential as that of charge and to that of infinity. Okay, so it is insulated uncharged conductor. Okay, so it is not insulator charged conductor, it is insulated. Okay, insulated means It is insulated basically to prevent the leakage of the charge, okay, or transfer of charge from one conductor to another conductor. Okay, that's why it is insulated. It is not insulator, it is insulated to prevent the transfer or leakage of charge from one conductor to another. The magnitude of electric field intensity is related with the electric potential as E equal to minus dV by dr. Does the electric potential difference between any two points, say A and B, in the electric field is given by? Okay, so electric field is related with potential with this relation. So between any two points in the electric field, between any two points, we take A and B, the potential difference is given by like this. This is potential difference between any two points equal to minus E dot dr from point A to B. So this term dV integration is known as potential difference, whole potential difference between two points A and B, VA minus VB, equal to minus A to B E dot dr. So this is the relation potential difference we can find between two points where E is the electric field exists there, and from point A to B. Potential decreases along the direction of electric field, that we know. Okay, electric field is in the direction of decreasing potential and becomes zero at infinity. Okay, potential becomes zero at infinity. Hence, potential at the location of uncharged conductor will be intermediate to the potential of charged body and infinity. So, because that uncharged conductor is placed between charged conductor and infinity, so it will have potential greater than infinity. Okay, so at infinity it is zero, so it will have potential difference greater than zero, and it is placed between the charged and infinity, charged conductor and infinity. So potential on that uncharged conductor will be less than that of charged conductor. Okay, so it will be intermediate to the potential of charged body and infinity. Okay. So next question, calculate potential energy of a system of a point charge minus Q placed along the axis due to charge plus Q. So there is a plus Q charge that is uniformly distributed along a ring of radius R. So there is a ring of radius R and this plus Q is uniformly distributed over the ring of radius R, and there is minus Q charge placed on the axis of that ring. Sketch PE. Sketch potential energy as a function of axial distance Z. So we have to draw a graph which shows the relation of potential energy with the axial distance Z from the center of the ring. So this Z is the distance of this point where minus Q charge is placed from the center of the ring in the axial direction along the axis of the ring. Looking at graph, can you see what would happen if minus Q is displaced slightly from the center of the ring? So what would happen if minus Q, small charge, is displaced slightly from the center of the ring along the axis? So I will give you some time to think about it. So let's see the answer. Let's take a point P at a distance Z from the center of the ring as shown in the figure. So this is the figure. This is ring and capital Q charges uniformly distributed over this ring, and this dq, small dq, this is the charge on the small element that we are taking for the deriving an expression. This small element of the ring, that dq charges of the small element of the ring that we are using to derive the relation between potential energy and the Z. Z is the distance of this P point from this center of the ring. Okay. So the distance of this element from this P point will be, according to Pythagoras theorem, Z square plus A square. Okay. The charge element dq is at distance Z from point P. Therefore, V can be written as, so V can be written as V equal to KE integration dq by R. So this R is generalized form of, what is this K dq by R? This is the potential at point P. Okay, the charge element dq is at distance Z from the point P. Therefore, V can be written as V equal to KE integration dq by R equal to KE integration dq by Z square plus A square. Okay, so this R is the distance of P point from the element dq. Okay, so that distance is R, which is Z square plus A square root. That A is the radius of the ring. So where K is 1 by 4 pi epsilon naught. Okay, so how it came? KQ by R. Okay, so this is the potential. What is potential? KQ by R. So here we are taking dq because we are firstly taking the potential due to small element of the ring. Okay, so small element of the ring having charge small dq. Okay, so this dq is the charge on the small element of the ring, and by integrating we will find the potential at point P due to whole ring. So that's why we are integrating. Okay, we want to find the potential at P point due to whole ring. We are finding just for small element now. Then we are integrating it. Okay, so integrating it, dq by what is R is the distance of element from the P point, that is Z square plus A square root. That A is the radius of the ring, where K is 1 by 4 pi epsilon naught. Since each element dq is at same distance from the P point, so since ring is symmetric, so each point, each element on the ring is equidistant from the P point. So we have net potential V equal to, after integrating dq, it will become Q. Okay, charge on the whole ring. Okay, Q. After integrating this dq, small dq charges, it will result in capital Q. That is the charge on, whole charge on ring. Okay. So this ring is symmetric about an axis. So if we take any element, if we take this element, this will also at same distance from this P point. Okay, this element is also say at the same distance from P point. If we take this element, this will also be at same distance from this P point, because this ring is symmetric. Okay. Considering minus Q charge at P, the potential energy is given by, now we have found the potential, now we will find the potential energy by considering minus Q charge at P. So we will simply multiply potential difference that we have calculated with the charge, that is minus Q here. So potential energy is 1 by 4 pi epsilon naught A minus Q upon 1 plus Z square by A. Okay, so this is the equation. You can see this. You should not emphasize on this if you are not understanding it. You should emphasize on that. KEQ minus Q upon root Z square plus A square. Okay, so this is U, this is Z. Okay, so how this graph came? Now put this Z equal to 0. When Z equal to 0, this potential energy will have maximum negative value. This is negative sign, na? So it will have maximum negative value. When this Z will have some value, then this new denominator becomes large due to the Z value. That's why potential energy will become small. As this Z increases, this potential energy will decrease. When this Z will be equal to 0, then potential energy is maximum in the negative direction. So this type of graph will be formed. Okay. So the answer for second question, what will happen if we displace the minus q charge along the axis by a small displacement? Then what will happen? The variation of potential energy with Z is shown in the figure. I have explained this. So the minus q charge displaced would perform oscillation. So it will perform oscillation. Why? If we displace the charge, suppose if the charge at center of the ring, okay, so from the center of ring, if we displace the charge from the center of ring along the axis, at center of the ring, charge will have minimum potential energy, the most negative potential energy, minimum potential energy. So it is in stable equilibrium. If we will displace it through a small displacement in this direction, so its potential energy increases in the positive direction. It will become less negative. So it will again try to come at the minimum potential condition. So it will go there. After going this direction, it will go there in this direction. So it will oscillate across this minimum potential value, minimum potential energy value. So it will perform oscillation, okay, to attain the minimum potential energy condition. So the next question, calculate potential on the axis of a ring due to charge Q uniformly distributed along the ring of radius R. So let's see. So it is similar to the previous question. Now we have to find the potential. Okay, so similar steps will be taken. Let us take a point P at a distance x from the center of the ring as shown in figure. The charge dq is at a distance x from point P. Therefore, V can be written as. So again, similar, only Z is replaced by x. Similar steps. So V equal to Ke integration dq by R equal to Ke integration dq by x square plus a square. So Ke equal to 1 by 4 pi epsilon naught. So refer to the previous diagram. We have to find the potential now. Okay, so same steps, similar steps. Only Z is replaced by x. Okay. Since each element dq is at same distance from the point P, again ring is symmetric. So that dq element will be at same distance from point P. So we have net potential, that is Ke upon root x square plus a square integration dq. So integration of dq will become capital Q. So this is the diagram, same diagram again. So this is x, this is a, so x square plus a square root. Okay. So the net electric potential will become this 1 by 4 pi epsilon naught Q by x square plus a square. Okay, so potential energy we can find by multiplying the charge on this P point. If the charge is positive, then potential energy will be positive. If the charge is negative, potential energy will be negative. So the direction of graph also changes according to that. If charge is negative, potential energy graph in the negative direction. If charge is positive, potential energy graph will be in positive direction. Okay. So thank you. I hope you enjoyed the session.